Okay, so yeah, now it's working. Actually, my stylus gets disconnected every time, and whenever I connect it, it hangs the PowerPoint. So that's why this issue is happening. Okay, anyways, so welcome to the 32nd lecture on power system operation and control. And till now, we were discussing all about operation of power system. And now we are jumping towards the control part, and probably I'll take around 7 lectures, and then with that we will be able to complete this course. So we have around 42, 10 more, including this 11 lectures remaining. So yeah, probably 7 to 8 lectures I can take, and then I can finish this control part and get you the understanding how you actually control the active and reactive powers in a power system. So both we are going to see in the coming up lectures. So this is all going to be about that, and at the end we will be seeing some part basics concept of SCADA, which will come at the end. Probably one lecture I'll take, and I'll give you a flavor of what exactly SCADA is. But yeah, with this we are almost towards the end of the syllabus, but let's go ahead and discuss about the control part first. So before we jump, let me just quickly recap what we have studied previously. In our previous lecture, we were talking about the Lagrangian relaxation based dynamic programming of unit commitment method. So we were discussing all these assumptions, what we are making, how we are forming this q lambda, how we are decoupling the coupling constraints in the LRDP method. We discussed about that, and we also discussed the algorithm, how exactly we have to solve it, and we discussed about the basic concepts of dynamic programming, how actually it moves from one step to the another step. I'm just giving you an idea. There are different types of dynamic programming. There are forward DP and backward DP. So the thing which we were discussing was in this direction, so that's why it's called as forward DP. But there is another method which actually sees from the last to the first, so that is called as backward DP. Both has its own pros and cons. Both ideas are basically dependent on the same logic, so it depends on the user how you want to implement. But what we have implemented here, it is the forward LRDP method. So then we gave you an example to solve how this algorithm has to be implemented, and then I gave you the idea how exactly you will add the penalty function on that, and then you will implement that part, and eventually how you will converge the iteration and how will you stop the iteration. And yeah, so did anybody try this example or not yet? Or any queries on LRDP method as of now? So because we will be ending this chapter or this section of our course, and we'll be moving towards different, altogether different methods and different concepts. So it will be better if you can clear your doubts at this level. Okay, anyways, we will be seeing this example today in the tutorial session again, and we will be quickly I'll not solve it. I'll give you a quick idea and how to proceed. Probably one iteration or so I can help you out in solving, and then you can later on solve in your tutorial for around 2-3 iterations. And also I'll give you today on during our tutorial session the flavor of MILP. So this I'll give you an example of it. It's a very interesting method the way they handle this binary or the status of the generators, how they are taking care of that. There is an algorithm for that. It is a very interesting method. So I hope you will enjoy learning that. Okay. Any queries, or shall we go ahead on the control part? Okay, if no queries, then let us go ahead. So, whatever problems we have discussed till now was on the operation part. And let's say if I just simply explain you based on the timeline. So let's say if the longest problem is basically LR, long range hydrothermal scheduling problem, then it will be short range hydrothermal scheduling problem, then you will see unit commitment, then you will see basically you can basically DCOPF, ACOPF, and ED you can all draw in the same line. Even SCOPF you can draw all in the same line. So this long range is probably from 1 year to months. This can be from 1 day to some months or 1 month. This unit commitment is generally for 1 week to 1 day, and this is for hourly or minute basis, right? Now, what happens if, let's say, change is happening in a smaller duration? So till here, what we were seeing here is basically we are just giving the generators a signal that okay, you have to generate at this value, and this value is going to be economical or secure for the complete power system, right? So this is what we are doing in this. Broadly you can say we are just talking about economics or security, economics and security. So this in complete whatever this LRHTS, short range hydrothermal scheduling, unit commitment, ED, DCOPF, ACOPF, SCOPF, here all we are giving just a signal to the plant operator or the generator operator or to the generators in a broad sense that okay, you have to operate at this value. Now question comes, how he is going to operate at this value. So basically what he is going to do, there are some controllers, some reference set points, some control actions are there with the plant operator, and he can change those settings, and by changing those set points he can tell the generator okay, now you have to operate at this value, you have to ensure that the frequency is at a nominal value, you have to ensure that the voltage is satisfied, the voltage remains at a particular value. So all those things will happen in a very small time duration. So here we are talking this part is all few seconds to few minutes. So here whatever step we are going to see, here we want our generators to control the system or to give that control signals and to react to those control signals at a very fast pace. Here we want it to happen in few seconds or max to max in few minutes, not more than that. And specifically, if I say the few minutes, when I say, it is not more than 15 minutes, it has to be less than 15 minutes. In Indian context, in US context, it is 5 minutes. So there the control actions are even faster. There they have 5 minute time window, so they want this control action to be taken in, or to be completed rather, because the control action you have to take, then the controller will react to that action, and then gradually it will stabilize the system. So that complete process has to happen in 5 minutes in US context. But in India, we have some liberty. We can stabilize the system in 15 minutes, till 15 minutes, but obviously it has to be less than 15 minutes. Right. So basically, what all are the control actions what we were giving till now to the generators? We did this ED, we did the DCOPF, we did this ACOPF, we did this SCOPF. In every stage, from here to here, here to here, here to here, we are passing on some or the other inputs. Right? Can you tell me quickly what all inputs we are passing on? Anyone? And what is the main input what we are giving here?
I think the variables of generators, PG, and in economy dispatch, lambda is there, and in unit commitment, startup and shutdown value, and hydrothermal, there is water discharge. I think this.
Good. Yes, exactly. So we are giving the water discharge values. Let's say I'll write Q here. Here we are giving on-off status. Let's say I'll say U. U is the status of the generator. In economic dispatch DCOPF, we were giving PG values. Right. There is one more thing which we are giving. You can also say we are giving voltage. Right. So basically two things which we are passing on to these fine-tuned control actions, and that is PG and voltage. PG is the real power generation what a generator has to do, and at what voltage it has to generate, that has to be maintained. Right. If you, let's say, if you are the power plant owner, your total job to maintain in the, total job at the power plant is to just satisfy this, whatever the generation value is given by the system operator. So all these steps what we are talking here, it is all performed by system operator. So basically, whatever PG values a system operator is giving to this power plant owner, it has to just satisfy that PG value. It has to tell its generator that, okay, you have to generate this PG value for this time window or for this time interval, and you have to maintain this particular voltage for this time interval. If those two things are satisfied from the generator, then obviously all other factors or all other studies, you can take care of those studies in a very simple manner. And why it is simple? Because we just, if you know the PG value from a generator, if you know the voltage value of the generator, then you can easily solve the power flows. Right? From a generator in a power flow we say generator bus is a PV bus. Why we say PV bus? Because we want a generator to tell us its P setting and its V setting. V means the voltage setting. And if you know the P and V setting of the generators, then you can easily, and you know the load values, the P and Q values of the loads, then you can easily perform your load flow. And all the power system studies, any power system study you take, every power system study starts with a load flow, start with a power flow. Either you have to do fault studies, either you have to do the protection related issues you have to resolve, either you have to do some economics related thing, either you have to analyze the system for any purposes, you have to ensure that the line limits are followed. For every study you take in the power system, eventually you have to run a power flow. That is the very basic fundamental, and that's why you will see in your bachelor's course also you must have studied power flow, because power flow is the basic of all the studies in power system. So here in this state, here in this control actions, the generator will always try to ensure that the PG and V are satisfied or set at a value which is given by the system operator. And if all the generators are following the system operator's orders, you can say it in order sense because it is mandatory, whatever system operator says a generator has to follow, then obviously everything will remain at a planned manner, because system operator has to ensure that all the lines are within limit, there is no voltage violations, everything is satisfied. So if all the generators are following its orders, then obviously the system will remain at a stable state. So we are going to see these control actions here, what exactly the power plant operators do to satisfy this PG values, to satisfy this voltage values, what all actions, what all changes it has to do in the power plant, that we are going to see in this coming up lectures, probably 5, 6, 7 lectures. Right, so I hope you got the basic idea what we are going to see in the coming up lectures, and we want these actions to be very fast because obviously because in every 15 minutes you will again get new signals by system operators, because in India it is a 15-minute time window. So every 15 minutes you are going to get different signals, and as soon as you get different signal, the previous signals is not valid, so therefore you have to act very fast to bring the system back to normal state. So I hope you got the idea what we are going to see in this course. Now let us see this in here. I'm mentioning this word steady state. What does this mean is, although we are including the effect of changes, we are going to see how the load is going to change, and then because of the change in the load, how the system operator is going to give new signals to the power plant, and then power plant operators are going to react to those signals. But in all these process, we are assuming that some complete system remains at the steady state. We are not going into the dynamics, we are not going into the transient state of the system. Transient state means basically the oscillations, because we are assuming if you have studied in the control system course, if you have studied it before, then you know that whatever changes you do in the control actions, there will be some oscillations and it takes some time. So there will be some oscillation and gradually it keeps goes and settles down. But we are not considering this oscillations. We are assuming that these oscillations are, whatever oscillation is happening, it is eventually settling down at a particular value. So that's why I am assuming that it is a steady state. These oscillations comes under transient studies, and this probably Professor Kumbhar is actually teaching you the transients of power systems. So I'm not going into that. This is the other part. So again, I just wanted to clarify here, whatever control actions we are going to study here, we are studying based on the steady state, not on the transient state, right? So I hope you got that. I'm just trying to set up the background so that you get the idea of what we are going to study in the coming up lectures. Okay, so just quickly want to go through these sentences. So till now we were looking at the normal operating states of the power system. Now in this problem we are going to see some closed loop control will be there, and these closed loop control will be a continuous closed loop control, and these control loops or these loops are going to eventually satisfy all the criteria of the generators or required from the generator. So basic idea is very simple, that there will be, we cannot control the demand, right? You never, we never think before switching on our fans, switching on our tube lights, switching on our air conditioner, switching on our any appliance. We never think about that. So that means at every fine tuned seconds, some or the other load is continuously changing, and these small changes in the loads, we cannot predict it. It is unpredictable. So basically, this small change in load, which is happening at every 15 minute, between 15 minutes, let's say in every second, the load is continuously changing. And with all these change, we still want our system to work. We still want our system to remain at a stable point. We still want our system to satisfy all the basic criterias. So basically, here in this control action, obviously here in, let's say if we talk about LRHTS, here we have some prediction, some forecast about the loads. Based on that, we are studying it. In SRHTS, we also have some prediction. Obviously, as the time comes closer, the prediction becomes even accurate, right? So still there will be some error in SRHTS, and then there will be some errors, and then we will go for unit commitment. Here we are going for 1 week or 1 day, so obviously the prediction will be even good, even accurate, and then we can easily study the unit commitment and get the status of the generators. And then when we are going for ED, DCOPF, ACOPF, SCOPF, we know that we are running it hourly or a minutely basis. Then basically the accuracy of the load change is even accurate, and we can easily predict the load change at a short time duration. So basically, all these studies what we are doing, it is all because of load change, right? So whatever load we are changing at every time interval, and we want the load to be known exactly, then only we can run the system accurately or perfectly. If we do not know the load, then we will not be able to run the system. So all these deviations, all these uncertainties are actually leading to the change in the demand, and with this change in demand, it is difficult to balance the system. So therefore, we are actually in the power system operation, we were actually running all the power balance equation which we are satisfying, that was based on prediction and some forecast. But as we go or come close to the real time, this week you can say actually the real time. So at this moment, let's say if some load change, what will be the actions of the generator to satisfy that load? And obviously now you are not talking about economic dispatch, we are not talking about economics. So economics is till here, so I can actually differentiate that all these on the left hand side, this is all talking about economics, but here on the right hand side is only to satisfy some criteria of these of power system. We are not focusing on economics anymore. So obviously if system runs first, then only you will think about economics, right? If system is not able to operate, or if it remains at unstable state, or if it goes to a blackout situation, obviously your focus will not be to go for economics. You will first want the system to run, and then you focus on economics, right? So all these actions or whatever we are going to see here, it is all because of demand deviations. And who is changing that demand? We as a user, we are continuously changing that demand. And here you will see I'm adding this word automatic control. That means generally system of even the power plant owners, they do not touch the power plant. Generally these days the process are very automatic and advanced these days. Generally system operator, even power plant owners, they do not touch or tell the power plant what to do. It automatically sense. They have lot of sensors, lot of measurement devices, and they sense those changes and automatically reacts based on that, and it satisfies all the criteria in a real time manner and a very quickly and effective manner. Now I was continuously telling there is some criteria which has to be satisfied. Can you guess what all are those criterias? What criteria I'm talking about? What satisfy? What will be the action which will suggest that the power system is operating at a satisfactory level? What will be that criteria? Anyone?
I think voltage limits and power limits
Voltage limits,
and
yes. Okay, good. One is voltage limits. There are two
speed,
criterias.
speed of controller.
Speed of controller. Okay, you can say that. Obviously, it has to be very quick. So mostly it is ignored because they are generally very quick. Uh, but there is,
Frequency.
huh? There is one more thing which we want to satisfy, and which was we were ignoring till now. There is one factor which we were ignoring till now, and now we are going to discuss about that.
V over F ratio, flux. V over F ratio.
Sorry, come again.
V over F.
V over F. What is V? What is F? What is
I
V?
think it is related to the excitation system. Or you can see voltage.
Sorry, what is V? What is F?
It is flux. I think it
Sorry, your voice is breaking.
later.
Baldin, your voice is breaking. Can you repeat what is V? What is F?
V over F. I think it is the flux. This percentage is flux. Flux.
Oh, flux. Okay, you're talking about flux. Not exactly, not directly, but yeah, indirectly, yes, flux will be there. There will be some impact of that. But anyone else want to try? One, what Baldin has said is correct, that voltage we have to satisfy. There is another parameter which we want to satisfy in this short duration. What is that? And the complete
Frequency.
perfect, perfect. Yes. So we have to focus on voltage and frequency. These two parameters, if we are able to satisfy, because all, again, just want to recap this, all our appliances, whatever appliances you have, you will see that there is a set of or range of voltage within which it will operate efficiently. There is a range of frequency within which it will operate efficiently, or rather range of what it is. If you have frequency exactly at 50 hertz, it will operate the most efficient way. And in US, because it is 60 hertz, there all those appliances operate at 60 hertz. So for example, if you take your Indian appliances and if you go to US and connect your devices there, you might be able to see some weird operation of those devices, because those devices are meant for operating at 50 hertz, but in US it is 60 hertz, so you'll see some difference in operation of those devices. So for example, let's say specifically all the display, let's say if you take your laptop, if let's say you buy a monitor in India and you use that in US, or you buy a television specifically, because there you can easily see the difference and the fluctuations. If you let's say buy a television in India and take it to US or vice versa, you will see that the display, there will be some grains and some light fluctuations which you will see in the television and in the monitor, and that those fluctuations is not good for those appliances, because it will actually damage the appliance and it will gradually reduce the life of the those appliances. So basically, we are going to focus on voltage and frequency, and we are going to satisfy that in this complete lectures what we are going to see in under the control part. Now let us go to the next slide. As you guys have correctly guessed it, that when we talk about satisfactory performance of power system, we always talk about voltage and frequency, because all our appliances operate based on these voltage and frequency. So now my question is, why if you see some of the appliances, let me just quickly give you, let's say talk about frequency first. If you see that if we do not maintain the frequency at 50 hertz, we all have, if you see your fans, if you see your air conditioner, if you see your refrigerator, in every these appliances you have induction motors, and these induction motors, the operation of induction motors depends extensively on frequency. The losses, the eddy current losses, the hysteresis losses, they also depend on frequency. The EMF generated, the back EMF generated by these motors depends on frequency. So all these parameters of these appliances will start deviating from its efficient point, and it will not operate at that efficient level. So basically, therefore, you have to maintain the frequency at 50 hertz. Auxiliary systems. So let's talk about auxiliary system for a while. So basically, here this auxiliary system, I'm talking about the auxiliary system of a power plant. So obviously, for to run the power plant, there are a lot of, in background, there are a lot of small devices which are connected, which supports the power plant to run efficiently, and those devices, they also depend on the frequency. So if, let's say, if the frequency is not appropriate or not at a 50 hertz level, then those devices will not operate at the efficient level, and eventually it will not allow the power plant to operate at efficient level. So there will be some differences, and at times these differences are huge. So therefore you have to ensure these auxiliary systems are operating at a proper efficient manner. Also, obviously, you know that if the frequency, specifically if the frequency is very low, there will be high magnetizing currents in motors and transformers, which will eventually lead to the high losses in the motor and transformer, and because of that, the motor and transformer can get damaged, because those laminations can get damaged, and eventually the life of the motor and transformer will reduce. There is electric clocks. Anybody aware of this electric clock? Have you ever seen this electric clock anywhere? Any idea what is electric clock? So, yes.
It's related to thermocouples and this.
Sorry, come again, please.
It is related to controlling the heat in industry.
Exactly, it can be means there are a lot of applications for that electric clock. The basic idea of electric clock is simple, that obviously in regular clocks, let's say you see your wristwatch or your wall clock, whatever you have at your home, you just see that in clock, to show the time accurately, what is needed? What is needed from a clock to show the time accurately? Can anybody guess? It is not power system. It is, I'm talking very general sense. To run a clock accurately, the simple idea is the hand, the second hand, the hand which is, or the second hand, because in the clock there are three hands: second hand, minute hand, and the hourly hand. So in the second hand, if that second hand moves correctly, means the 1 second of the second hand actually moves exactly for the 1 second, then you can ensure that the complete clock operates at the clock basically shows the right time. So for example, let's say in your wristwatch, generally you will see, if you have if you have bought a wristwatch before, you'll see that in olden days you used to get quartz wristwatch. I don't know if you have heard that term or not. Quartz wristwatch. So basically, quartz is a substance, it's a material which actually fluctuates at a frequency, and based on that frequency we calculate that okay, what will be that frequency, and we can convert that frequency into seconds. Similarly, let's say in olden days you must have seen the clocks which has screws. You have to tighten the screw, or basically you have to give means tighten the screw and gradually it runs. As soon as you give a screw, then it runs. So basically in the background inside that clock you have actually springs, and once you tighten this screw, it actually tightens those spring, and gradually it spring releases those energy, and obviously the rate at which it is releasing that energy, the way your clock will operate and the second hand will operate. Similarly, these electric clocks in back in olden days, the electric clocks were used, especially in India. I know, I'm not sure about the other countries, but in India, in railway stations, as most of the railway stations were having these electric clocks. And basically, we know that India is 50 hertz. So you can easily calculate the time. It is basically 20 millisecond. So in 20 millisecond it takes 50 hertz. So you can imagine, if the frequency is 50 hertz, then that means it is 20 millisecond. So basically you have to have 5 cycles, right? So if you have 5 cycles, it will be 100 millisecond and it will be 1 second, right? So 100 millisecond is equal to 1 second, right? Or am I incorrect? Right. So you got the idea, right? So basically if the frequency remains at 50 hertz, then we are getting a time interval of 20 millisecond. So those clocks were in the background having a sensor which actually just sense the frequency, and based on that it sense the time. And basically if you see in olden days, these frequency obviously were not exactly at 50 hertz. They used to deviate a lot, and because of that the time which we used to see in olden days was also not correct. They were also basically you can see that, I'm not sure if you know this or not, every day or 2 or 3 days or in every week, people, your parents or grandparents, used to match the time with the radio time, or basically in radio they tell that what is the time right now, or in television they used to tell in olden days, and then we used to match the time, and then from that it starts operating. So basically though that is electric clocks. And when these electric clocks were used, right now obviously these are not used, but in olden days electric clocks were very popular and people used to use this, and it used to operate based on the power system's frequency. And as the frequency was not a constant, or was not at 50 hertz, it used to give a very inaccurate timings. So this was the another so yeah, obviously whatever application you can choose, there were a lot of industry which were also using these electric clocks, and lot of applications were there for this. So basically you can imagine people used to keep the idea of time based on the frequency. So it was that important in the olden days. Now let's come to the voltage. Why voltage should remain within an acceptable limits? So some idea is basically, if you keep a voltage outside its limit for a longer duration, obviously it will over voltage or under voltage, it will lead to excess of damage inside the appliances or in any motor or in any machine. It will create issue if you operate in over voltage or in under voltage state. Voltage also leads to system stability. This is again connected with the brownout. I hope you remember I explained you the concept of blackout and brownout. So system stability is also affected because of this voltage. If it does not remain at the particular value, obviously the loads are dependent based on voltage. So if voltage is not at a nominal value, then loads will also change its behavior and its power consumption. And if the load changes its power consumption, then generator has to adjust to satisfy the power balance, and eventually this iteration keeps on happening, and eventually the system has to remain at stable, but it depends. At times it remains unstable, at times it goes to instability. So I explained you the concept of brownout. You can imagine from that. I hope everybody remembers the concept of brownout. Now, the next is basically the real and reactive power losses in the system also change based on the voltage. So, obviously, you know the current flows based on the difference in the voltage, and if the voltage is not proper or not remain within the limit, the losses may increase, and which will further reduce the efficiency of the power system. So a lot of factors which can affect the system, and in all those factors, if you are able to satisfy the voltage and frequency at a particular rate or at a particular nominal value, then you can assure that your system will work in a efficient manner. So you can see that it's very simple, right? You just have to focus on frequency and voltage. Everything is going to be satisfied. So any query as of now? So also, huh. So there are two things. Just from this frequency and voltage point of view, you have studied this fast decoupled load flow in power flows in probably in your CAPSA course or in your bachelor's course. You know from that QV coupling is very strong and P delta coupling is very strong. And if you will see that Q, obviously the reactive power affects the voltage, and if you are not able to satisfy the real power, then it actually affects the frequency. So basically, to satisfy the frequency or to satisfy or to keep the frequency at 50 hertz, we have to play with the P or the real power generation. And to satisfy the voltage or to keep the voltage within a particular bound, we have to play with the Q, or that is the reactive power. Although practically they are not completely disconnected, there are some connections. We cannot completely ignore that there is no connection. There are connections, but obviously their strong coupling is there. But you can easily observe from the power flow point of view that the Jacobian matrix on the off diagonal elements are basically very loosely coupled. So you can imagine from that we can exploit this opportunity and see that there is a significant decoupling between those two terms. So we are going to focus on this P and Q in this complete course. So this control of in the title of this course lecture, I mentioned that we are talking about control of active and reactive power. Basically, we are focusing on control of voltage and frequency. So voltage from the reactive power, frequency from the active power. So this is what we are going to see in this coming up lectures. And this lecture was just to give you a background and what we are going to see in the coming up lectures. I hope you got the idea, and because the next slide is going to